Hi, my name is Edward Kemei, and this is my Unit 4 case presentation. This is how my name is spelled. I will be presenting case number 2 and case number 1 and case number 2. Case number 1 is about the infant with high ammonia. During amino acid metabolism, ammonia is generated and needs to be removed from the tissue to prevent toxicity. This is a general amino acid molecule. The amino group is responsible for ammonia production. Before I proceed further, I would like to discuss the process of transamination. This is where an amino group is transferred from an amino acid to a keto acid. This reaction does not free ammonia, and it needs transferase enzyme and pyridoxal phosphate. As shown here, this amino acid, an example is alanine, interacts with keto acid, an example is ketoglutarate, to produce a different keto acid, an example is pyruvate, and a different amino acid, an example is glutamate. Transferase enzyme in this case is alanine aminotransferase. This is a general overview of ammonia transfer. In most tissues, ammonia produced from amino acid metabolism interacts with glutamate to form glutamine using glutamine synthase enzyme. Glutamine form is a non-toxic ammonia carrier, and it will transport ammonia to the liver. In the liver, glutamine deaminate is deaminated by glutaminase to produce glutamate and one molecule of ammonia. Ammonia produced enters the urea cycle. Glutamate is deaminated by glutamine dehydrogenase enzyme to alpha ketoglutarate, releasing additional ammonia molecule. This additional ammonia molecule enters the urea cycle, whereas alpha ketoglutarate and the citric acid cycle will be involved in another transamination reaction. In the muscle, ammonium ion is fixed by glutamate dehydrogenase to generate glutamate. Pyruvate from gluconeogenesis or from glycolysis interacts with glutamate to produce ketoglutarate and alanine. Alanine is a non-toxic ammonium carrier, transports ammonium through blood to the liver. In the liver, alanine undergoes transamination with ketoglutarate using alanine transferase as enzyme to produce glutamate and pyruvate. Glutamate is deaminated by glutamate dehydrogenase to form ammonia and alpha ketoglutarate. Ammonia produced in the urea cycle and ketoglutarate produced will be used in citric acid cycle. In faster state, pyruvate and alpha ketoglutarate produced in transamination are used in gluconeogenesis pathway. As you can see here, pyruvate is carboxylated by pyruvate carboxylase to produce oxaloacetate. Oxaloacetate is then reduced to malate by NADH. Malate diffuses out of mitochondria to cytosol, where it's oxidized back to oxaloacetate, and then it's acted on by phosphoenopyruvate carboxykinase to produce phosphoenopyruvate. equilibrium reaction then continues in favor of glucose production because of low glucose in faster state. Alpha ketoglutarate enters into citric acid cycle as well and goes through a few steps to produce malate, which diffuses again to cytosol and goes through the same pathway to produce glucose. In a case like this, where ammonia is elevated with elevated orotic acid, accumulation of carbamyl phosphate and is being fluxed through into the cytosol into the pyrimidine synthesis pathway. Since there is an excess carbamyl phosphate synthesis 1 is less likely or is least likely to be deficient. Given that citrulline is 10, which even though it's indicated as normal, it's actually in the lower part of normal range. It can be inferred that ornithine carbamyl transferase is deficient. Given that citrulline is borderline low, downstream amino acids are likely to be also low, which means if this situation persists, arginine will now become essential amino acid. In case number 2 scenario 1 is about an infant with branched chain amino acid in the urine. This is also termed as maple syrup urine disease. Branched chain alpha ketoacid dehydrogenase is the enzyme that is likely to be deficient in this case. Therefore, the branched chain amino acid valine, leucine, and isoleucine are not metabolized to its products and they end up accumulating. Branched chain amino acids are already essential and cannot be synthesized in the body. Therefore, one of the therapies for maple syrup disease is avoiding proteins in diet in order to reduce the amount of valine, leucine, and isoleucine. Thiamine or vitamin B1 can be potentially useful supplement as it is a cofactor for branched chain alpha ketoacid dehydrogenase, which will assist in potentially breaking down these branched chain amino acid to their final products. Case number 2, scenario 2 is about a 30-year-old female with symptoms that are consistent with alkaptonuria. Homogentisic acid oxidase is the enzyme that is deficient in this individual. Phenylalanine and tyrosine are no longer metabolized to acetoacetate and fumarate. There is accumulation of homogentisate, which is spontaneously converted to alkapton and excreted in urine. Homogentisic acid is also deposited in cartilages, causing joint pain and pigmentation in the cartilages of the ear. No amino acid becomes essential here because of the deficiency, and no therapy is effective for this condition. However, vitamin C or ascorbic acid was thought to be beneficial. It prevents the oxidation of homogentisic acid to benzoquine acetate, which causes darkening of the urine. Vitamin C, however, has been shown to increase the amount of homogentisic acid, which is basically counterproductive. Case number 2, scenario 3 is about an infant with increased level of phenylalanine. In this case, phenylalanine hydroxylase or its cofactor tetrahydroxybiopterin BH4 or both are deficient. Tyrosine is not synthesized here effectively and therefore it becomes conditionally essential amino acid due to the deficiency. Vitamin B6 or pyridoxal phosphate supplement which is a cofactor for transamination of phenylalanine can help by shuttling phenylalanine to produce phenylpyruvate and therefore preventing accumulation of phenylalanine.